In this video, we'll be talking about the velocity analysis of this particular problem, which you can see on the screen. You can see here we have the slotted lever mechanism, which is a kind of mechanism with quick return motion inbuilt into it. And we have been given all the dimensions here, and using these dimensions, we have been asked to find a certain things. So what is it that we are supposed to find? Let's first note down all the given data. So we have been given the length of OA, which is 400 mm, and we have OP, which is 200 mm, and we have AR, the length of which is 700 mm, and then we have RS, the length being 300 mm. So you can see that these lengths are very large lengths, and some of these cannot be actually drawn on the A4 sized sheet, which I'll be taking as a reference. So we want to solve all the analysis that we have been asked to do in an A4 sized sheet using the drawing instruments, and that's our challenge for today. So all the lengths have been given. AR is the maximum length, and let me just put this aside here to show you. Okay, so this, I'm going to take an empty A4 sized sheet, and this is where we'll be supposed to draw this particular diagram. So what you can see here is that the height of this sheet is 297 and the width is 210, and within this area of size A4, we should be able to draw all the diagrams and be able to do all the analysis that we are supposed to do. So this question is on acceleration analysis. And so we'll be supposed to find the acceleration of a few things. So first of all, you can see here we have been asked to find the acceleration of the point S, which is located here on the slide, and the angular acceleration of the link RS. So we also have to find the angular acceleration, that is alpha of the link RS. This we are supposed to find, and we need to find the acceleration of the point S with respect to any of the fixed points. So we can take it as G, or we can take it as O or A. So this we need to find. So we've been given the RPM reading here, the value of RPM reading, and it's rotating in clockwise direction, and all these are the dimensions. So we need to completely draw it over here. So for this, we will be solving it in 3 steps. First, we'll have to draw the position diagram at this particular instant, and then based on the position diagram, we'll be drawing the velocity diagram, and then finally we'll be doing the acceleration analysis for the same. So let's go ahead and see how big we need to make this diagram in order to conveniently fit here, as well as keep some space for the other diagrams that we are supposed to draw. So looking here, the length AR we can see is 700 mm, and I guess in this sheet we can easily draw a length of 14 centimeters. So this length, I'm going to take it as 14 centimeters, and for all other lengths I have to apply the same conventions. What I have done here is have multiplied by 2 and divided by 100 while coming from left to right. So the same I have to do for every other thing. So here we are going to take 4 centimeters, and here I'm going to take I'm going to get 4 times 2, that is 8 centimeters, and here 3 times 2, that is 6 centimeters. So these are the lengths I'm going to actually use in the diagram to draw this particular diagram, to draw this particular link. So let me go ahead and do that. So for that, I will need my drafter. I'm going to keep it somewhere here, and at 0 degrees, and I'm going to draw this length at 400 mm. So I'm going to take this, start here, and draw a vertical length of 4. Okay, 4. Okay, so the work of this is done, and I need to name this point. So let me just take this text. Okay, so this point here is capital A, and this point here is capital B. Sorry, not B, it's O, capital O. So these are the 2 points, and we got the first link here, AO. Now using this, we need to build the rest of the mechanism. So I guess I will next be needing my protractor, and I'll be keeping it in this direction from 0 degrees up. I need to build an angle of 120, which comes up here, and this length has to be exactly, how much is OP length. You can see it's got to be built as 4 centimeters. Okay, how much did I build this? Built this as 14. Okay, so let me see how much I built this. Okay, so I guess I made a mistake here. So even though I was asked to make 400 mm, I'm supposed to actually draw this as 80. So I'm going to just need to delete this, and I'll have to again draw this. So the length that we are going to draw here is 8 centimeters. So I'm going ahead and drawing 8 centimeters. So this point O is actually going to appear here, and at that point we actually need to draw, take the protractor over there, and I need to draw an angle of 120 degrees here. Okay, so that's 120 degrees, but the length here, the length OP, needs to be 4 centimeters. So I'll just take this, keep it here in that direction, and I need to cut this length over to 4 centimeters. Okay, so that will give me the point here called not only Q but also P. So Q and P both are overlapping here. And then I just need to join this, and then I need to extend it over till the length becomes 14 centimeters. So I'm going to go ahead and take this, I'm going to keep it here, keep it in this direction, and okay, I need to extend this line till I'm getting 14 centimeters right there. So that endpoint is going to be R. It's going to be R, so it's going to be capital R. Okay, so it turns out that space is not going to be enough, so I'll have to actually pull it down. Of course, when you're drawing with pencil, it's not going to be possible, so I suggest you adjust it in the beginning itself. So having a look at this diagram, you should be able to guess where exactly to start drawing it. So next up, we are going to take 350 mm at the top. We need a horizontal line from there, so I'm just going to place this over here, and okay, at what distance? That is 350. So 350, we again need to modify it over here, so we get to 3.5 and develop that is 7 centimeters. So I need to take a horizontal line at 7 centimeters, and then the RS length is has got to be 6 centimeters. So I have to take a circle. Or you can just in case you're using the drawing instruments, you just need to place it here at horizontal, and then you need to use a compass. To draw an arc of length 7 centimeters. Fine. So this is meeting here, so that's my final point. Now all these are just for construction sakes. I'm just going to delete it, and this point here is yes. So this is my position diagram, and this is the scale that I've used here, 2 by 100. That means I just have to divide by 50. I just have to multiply with this. This is not needed anyway. So this is the ratio I've taken. So in case I'm getting a length over here, for example the length AQ, we are going to need this length AQ. So if you want to measure that length AQ, which I'm going to measure it over here, so you can see the AQ length we are getting as 10.6 centimeters. So 10.6 centimeters. So that is the drawing dimension. So when we are converting it back, we will have to actually multiply 50 to this. So 10.5 multiplied with 50, that's what is going to provide us the actual length of this link. So that's coming out as 525. So 525 mm. So this is the length AQ, and what we have here is actually this particular length that we have taken. So since there is no measurement for this, I'm just going to keep it as unknown. Fine. So this completes our position diagram, and everything we need in the position diagram is now ready. So with this information, we got to start building our next diagram, that is the velocity diagram. So this here, what we have is the position diagram, and next what we have to start doing is velocity diagram. The velocity diagram we need to start. Okay, so in order to start the velocity diagram, I need to take the fixed points. I need to take all the fixed points, keep it at one place. And for velocity diagram, we are going to be using smaller letters. So I'm going to turn off this caps lock. So we have O, we have A, and we have the point G, all located at the same starting point. Now let's say what are the different velocities that we'll have to deal with. So first up, we have the velocity of the point P with respect to the fixed point O. So when we are drawing it in the line diagram, we are going to represent it as the vector O to P. So what will be its magnitude? Its magnitude will be dependent on omega times the length OP. So what is omega here? Omega we'll have to calculate using this value of 200 RPM. So that will be 200 into 2 pi by 360. So it's going to find that value. So 200 into 2 into pi, okay, divided by 60. So we are getting 20.94. So we are getting 20.94 in radians per second. So that is the value of omega, and we'll have to use that value omega over here, multiply the length OP to this. So when I say the length OP, you should not be taking the length OP from the position diagram, because position diagram is having some scale and we want the actual velocity. So we'll have to use the real world length of OP over here. So omega value, that's 20.94 multiplied with OP, the actual length of that OP, which is 200 mm. So we'll have to take that in meters, that it becomes 0.2 meters. Let me just push it a little to the side, and when we calculate this, what do we get? We get 20.94 times 0.2. So that's giving us 4.19, and this is the velocity in meters per second. So but when you are drawing the velocity diagram, we cannot take this value in meters per second. We'll have to take some value in mm. So once again, we'll have to apply some scale to this. So I'm going to take this as 42 mm. So when you are transferring, okay, so when you're transferring from this side to this side, the scale that I'm using is multiplying 10. Fine. So if you have to go from the drawing to the actual measurements, you'll have to divide it by 10. So that's our convention. So let's go back. So this is the thing. So we have got the first velocity. What will be the direction? Direction of that will be perpendicular to OP, and the sense is going to be upwards. So this is our first velocity. Similarly, let's find out all the other velocities that we'll have to either find, or either it will be given, and then we'll slowly start drawing the velocity diagram. So next velocity we'll have is the velocity of q with respect to the fixed point, that is a. And then we have velocity of the point p with respect to q, and then we have the velocity of r, with respect to a fixed point, let's say o. And then finally we'll have the velocity of the slider s with respect to some fixed point. You can take it as g, because g point here is as well fixed. So these are all the velocities we'll have to deal with. So how do we represent them in the vector diagram? This is going to be a line from A to Q. This is going to be a line from A to Q. Okay. This one here is going to be the line from Q to P. This one is going to be the line from O to R. And this one is going to be point from G to S. So notice how the alphabets are actually interchanging. So now let us see which of these velocities are known to us. So when we come to velocity of Q with respect to A, we know that it's going to be moving perpendicular to AQ. So it's going to be perpendicular to AQ. We don't yet know the direction, so it's just we just have to find it from the velocity diagram. So when we come to velocity of P with respect to Q, that's going to be parallel to AQ. And once again, we don't have the idea about the sense, so we're going to keep it as it is. Velocity of R with respect to one of the fixed points, that is going to be perpendicular to AR, and once again the direction we are going to keep it as it is for now. And the velocity of the slider will definitely be horizontal. So with this data we should be able to build our velocity diagram. So let's start with our first diagram, that is the velocity of P with respect to O. Okay, so let's take this up, and we'll have to first keep it in this particular direction. And because the velocity of P with respect to O will be perpendicular to this, we'll have to use this edge over here. So move your drafter to a particular point somewhere here. Okay, somewhere here, and we need to draw this particular length. The length is 42 mm. So let's go ahead and draw a length from here to 42 mm. Okay, so this is our first velocity. This is our first velocity. That is velocity of P with respect to O. The length we have drawn correctly, and at the other end of this, what should we get? So since OP is the length, this end here is going to be P. Next, we know the direction of velocity of Q with respect to A. So A to Q, A point is located here. So we need to draw a perpendicular to AQ. So let me take my drafter. I'll have to take perpendicular to AQ. So I'm going to clip it like this. And then I'll have to move this, keeping it parallel over here. So A to Q. So A to Q needs to be perpendicular to that. So I've kept it, this is parallel to this edge. So this is the perpendicular. So I'm just going to draw some length. I don't have any idea about the length or the sense in which it has to go. So I'm just drawing a length. Next one, I'll have to draw parallel to AQ. So I'll just take the same, and I will just move it so that it comes out parallel to this. So at this point, I know that my intersection point has got to be in the downward direction. So I'm just going to draw in this particular direction. So then we just need to shorten it up, and this point that we get here is the point Q. So one thing I forgot to tell you about at this particular point is that the point Q is located on this link, whereas the point P is located on the slider which is moving along with it. Fine. So So this clears that clears the velocity diagram for this particular things, and by measuring the lengths we will be able to find what is the velocity of p with respect to q, which is over here. So we'll first get that value over here. Let's go ahead and do the measurement. So velocity of p with respect to q, we can see that length is 27.5, because that length is between 27 and 28 mm. So that's what it's going to be. Okay, so 27.5. So this length here is 27.5 mm. So when we have to convert it back, so what happened when we did this conversion, we just multiplied with 10. So back here we'll have to divide it with 10. So here the velocity will be 2.75 meters per second. Similarly, let's go ahead and see what is the velocity of q with q with respect to p. So the value which we measured right now is for this one. Now let's see what is the velocity of q with respect to a. So velocity of q with respect to a will be represented by this length. Let's go ahead and measure that. I'm going to keep it this direction, and that's coming out almost 31, 32. So it's almost 32. So we're going to take it as 32. So 32 mm. So once again, when you have to convert it back, we'll have to divide it by 10. So we get 3.2 meters per second. So that's the velocity of q with respect to a. Let's go ahead and see how we'll be able to find the velocity of r with respect to o. So in order to find the point r, we will have to extend the length aq. So this length we need to extend it in the same ratio over here. So let's see how we'll be able to do that. So let's take the length aq, and we have the length small aq for that, and we have to take the length ar, and accordingly we'll have to generate the length small ar. So we know the length of aq, capital AQ, and we have measured that. And let's go ahead and use the lengths from the velocity diagrams directly over here for this. So the length aq, actually I think we have written it over here. So aq length we have 525. So let's take that 525. So aq length is 525. AR length we have found it, that is 700 mm. It's given actually. Let's take this as 700 mm. And let's see what's AQ length. We have found it, that is 32 mm. So that is 32 mm. So I'll take it as 32 mm, and this is the length we are supposed to find. So in this case we just need to multiply these two and divide by this quantity. So let's go ahead and do that. So 700 into 32 divided by 525, that will give us this particular length. Let's go ahead and use calculator to do the quick math. So 700 into 32 divided by 525, that's giving us 42.7 mm. So since I cannot exactly do that, I'll just round it off to 43 mm. So this AR, I'm going to take it as 43 mm. So I'll have to again take this the drafter. I'll have to keep it in this, not in that direction. Okay, I'll have to take it here in this direction. So I'll have to extend AQ. So A is here in the direction of Q. I'll have to extend it up to 43 mm. So 43. So this length needs to extend it to 43 right here. So now we can see that I've got another point over there, and that point is going to be small r. That's one point is going to be small r. So now that we have got the relation r, we need to go ahead and find the slider velocity. Now slider, we know it's going to be moving in horizontal direction with respect to the fixed points, and these are our fixed points. So we need to just draw a horizontal line from here. We don't yet know the length, so we're just going to keep it as it is. So somewhere on this line we are going to get the point s, small s, and we know the velocity of r with respect to s, velocity of s with respect to r, or r with respect to s, will be perpendicular to this. And so let's go ahead, take our drafter, keep it parallel to this, and we'll just have to move this, over here. So this is the line we will need. So let's go ahead and put that line over here. So that's it. So that's the intersection point we need. Let's remove it, and what the point that we get here, is the point s, and by measuring these values we will be able to find the remaining velocities. So let's see how we'll be able to get those velocities. Okay, so first let's measure the length OR. I think OR length we have already found that. OR or AR length is the one we found, and that's 43 mm. So here we have to get that as same, so 43 mm. So if you want to get back the velocity from this, it's going to be divided by 10. We have to divide this by 10 to get the velocity. So 4.5 meters per second, sorry, 4.3 meters per second is the velocity of r with respect to o. Next, let us find the velocity of s with respect to g. So that will be this horizontal length. So let me go ahead and measure that length. So I'll have to take the protractor, keep it horizontal, and we're getting that as 44 and 45, between 44 and 45, but it's nearer to 44. Let's go ahead with that. So 44. So this length we are going to take it as 44 mm. So when we convert it back, we will get 4.4 meters per second. So this is the velocity of our slider. That is the velocity of our slider. So with this we have finished doing the velocity analysis. Next we will have to go ahead and do the acceleration analysis, and acceleration analysis is going to be much more complex compared to this. So let's go ahead and do it. First up, I'll have to actually take this diagram. So since I'll be needing this diagram in acceleration analysis as well, so I'm just going to take this. Okay, copying and pasting it. Okay, we'll take it over here. You can see once again I'm getting this particular diagram. Let's just move it to correct position, and I'll have to start doing the acceleration analysis over here. So let us see what are the different accelerations that we have to deal with over here first. So we have first the acceleration of the point P with respect to O. Right, acceleration of point P with respect to O. This can be written as acceleration of P with respect to some other point, let us say Q, and plus acceleration of Q with respect to the fixed point. In this case, let us take it as we'll have to take it as O for now, and both O and A are fixed, so we can take it in any order we want. So we can just transform it like velocity of P with respect to O, velocity of P with respect to Q, and that's acceleration of P with respect to Q plus acceleration of Q with respect to the point A. Because O and A are both fixed, we can take it like that. Now upon closely watching this, we can see here clearly that acceleration of P with respect to O, since the velocity here is constant, So we will only have the centripetal acceleration of p with respect to O over here. Whereas here, acceleration of p with respect to q will have two components, and the first of that component is the linear component of velocity of acceleration of p with respect to q, and we will have the Coriolis component of p with respect to q. So both these will combine to give us the total acceleration of p with respect to q. Then coming over here, acceleration of q with respect to a will again have two components. The first one would be the centripetal component of q with respect to a, and then we'll have to take the tangential component of q with respect to a. So these are all the accelerations that we'll have to find. So let us try to find all of these one by one. Let us try to find all of these one by one. So once again, we will need a similar diagram to what we had done over here. So instead of for velocity, we will need the same for acceleration this time. So let's go ahead and get it. Okay, so something seems to be a problem over here. Okay, so I think it says in the other layer. Okay, so we'll need all this. So let's draw that over here, and let's first jot down all the accelerations one by one and their vector line. So first up we have acceleration of centripetal acceleration of p with respect to O, and this is also the total acceleration of p with respect to O, because tangential acceleration will be 0 here since there is no alpha, the angular acceleration here. So in acceleration diagram, we will have to start the acceleration diagram with the fixed points. Let me just move this velocity diagram up here, and we're going to take the acceleration diagram here. So acceleration diagram, we are going to start with again the fixed points. So in this case, we are again going to take the small letters. We are going to take the small letters, but not just the small letters, but we will have to place a subscript for all of these. We'll have to take a subscript for all these. So I'm just going to take the subscript. So the subscript that we will need here is 1. Okay, so 1 is the subscript, and we have to take the same subscript for all of these. So these are the fixed points, so they are going to overlap here at this particular point. So the notation, the vector diagram that we have here, it will be O1 to the final point P, so that will be P1. So O1 P1 will be representing the centripetal acceleration or the total acceleration of P with respect to O. So let us see if we are able to find it. Okay, let's go ahead and try to see if we are able to find it. So we know the formula for centripetal acceleration is velocity of P with respect to O, square of this divided by length PO. So we have to do that. So velocity of P with respect to O, we have already found it earlier. Velocity of P with respect to O, we can see here, that is 4.19. So let's take that 4.19 over here. So 4.19 square of this divided by the length PO. So PO length, we'll have to take actual length here, that is 200 mm, and that we need to take it in meters again. So when we convert 200 mm into meters, we get 0.2 meters. So we'll have to find the answer of this. Let's do the quick calculation. So 4.19 square of this and divide this by 0.2. So we're getting 87.8. 87.8. So now this is an acceleration, so its unit will be meters per second square. This is an acceleration, so its unit will be meters per second square. And when we want to draw this, we'll have to convert this into mm. So what's the most convenient length that you can easily draw on the A4 sized sheet for this particular thing? So I guess we can easily draw 88 mm. So we'll have to round it off, of course. So the length here that we'll draw will be 88 mm. So you can see here that the scaling factor is just 1. We don't have to actually convert anything. So whatever is the length, we can directly take it to mean the acceleration in meters per second square. So this is a value that we are going to draw in the acceleration diagram. What will be the direction of this? This will be the length we are drawing. The direction of this will be, if you see here the diagram, the centripetal acceleration will be towards O, and it will be parallel to OP, and it will be towards point O. So we were able to define the centripetal component of acceleration, or the total acceleration for the point P at this point. Fine. Now similarly, we'll have to go ahead and define all the other accelerations. Let us see which one of these we can actually find, which we can calculate, and which one of these we can just know the directions of. And then we will use this data to complete the acceleration diagram. And then by measuring the values in the diagram, we'll be able to find the accelerations. So let us see one by one. So this particular acceleration is over already. Let's go for the next one. And let's say this one. So linear acceleration of P with respect to Q. So we don't know how to calculate this yet. We'll have to measure the value from the acceleration diagram, but we know for sure that this will be parallel to the length AQ. This will be parallel to AQ, and we don't yet know the sense of that as well, so we'll just have to be satisfied with the direction at this particular moment, but we'll have to definitely give it the vector. So what is going to be its representation in the line diagram? So since it's starting at P, the first point will be P1, and from P1 we'll have to go to a temporary point, because the total acceleration is the sum of the two components. So from P1 we'll have to go to a temporary point, that is Q subscript P, and this will be parallel to AQ, and since we don't know yet, so we'll just keep it for now. Let's go ahead and see what is the next acceleration. So this is over. Let's take this one. So the next acceleration is the Coriolis component of the acceleration for P with respect to Q. So now the in the acceleration diagram, we'll be representing this from QP. We will start and we will end up at the final point, that is P dash, final point, that is P dash, or P1. So this is the Coriolis component. So we have the formula for this. That is 2 times velocity into omega. So velocity of which point do we need to take? That we need to be sure of. So this has got to be the velocity of point P with respect to Q, and omega will be the angular velocity of this particular length, this particular link, and that is AQ or AR. So AQ or AR. So that we'll have to take. So velocity of P with respect to Q, we already know that. Velocity of P with respect to Q, we know its value is 2.75. Let's take that here directly. So 2 times 2.75 in meters per second. And now this velocity we need to find. That velocity will again be velocity of AR. AR means R with respect to A, velocity of R with respect to A divided by the length RA. Right. So this will give us that particular velocity. Okay. In fact, we could have done that over here itself. Okay. so we'll have to cancel this and put it in its place. So velocity of r with respect to a, r with respect to a, or r with respect to o, it's going to be the same. So 4.3 we'll have to take it. So let's go ahead and take 4.3 here. So 4.3 divided by RA. So RA length, we'll have to take the actual length, RA or AR, that's given as 700 mm, which converted will give us 0.7 in meters. So 0.7 is what we need to take here. So you can see that we will be able to calculate its length. Let's go ahead and find it, how much it is. So 2 times 2.75 into 4.3 divided by 0.7. So that's giving us 33.8 when you round it off, 33.8. So this is again in meters per second square, meter per second square. Okay, so this is the vector, this is its value. Let's see what is the direction for this. Now once again, because the scaling factor is 1 over here, we just have to round it off to the nearest mm value. So 34 mm is what we will take it. And the direction, where will be the direction? So we'll have to first take the direction of velocity of p with respect to q, and velocity of p with respect to q, velocity of p with respect to q, it's going in upward direction, so we'll have to take that. So velocity of p with respect to q, and we will have to rotate it by 90 degrees in the direction of omega. So what is the direction of omega? That is the direction of omega. Since this is rotating clockwise, this will also be rotating clockwise, so we'll have to rotate it clockwise direction 90 degrees to get this. So this is our direction. So this is of course perpendicular to AR, and it's going to be going in that particular sense. So sense is also defined over here. Okay, so let us see what other accelerations are there. So at this point we have defined the Coriolis component as well. Let's go to the next component, the centripetal component. Okay, so now we need centripetal component of q with respect to point A. So we'll again be starting at the fixed point A. So we'll be starting from A1, and we'll have to go to a temporary point, and that temporary point will be q of A, q subscript A. So let us see if we are able to find this value. We know the formula for this. We know the formula as velocity of q with respect to A, square of this divided by the length QA. Let us see if we know all the values. So velocity of q with respect to A, we'll have to go back here. Velocity of q with respect to A, that's 3.2 meters per second. So that is 3.2 meters per second, square of that divided by length QA. So QA length, we'll have to take its actual length, mind it. So QA or AQ, that's 525 mm. So that's going to be 0.525, 0.525. So 0.525, because we are taking it in meters here. So doing the quick calculation, we will get its value, its magnitude as 3.2, square of this divided by 0.525. So that's giving us 19.5. 19.5. This is the value in meters per second square, and when we take it in the diagram, we can take it exactly the same in mm, because the scale factor is 1, as we have seen already. And now what about the direction? So direction for this is, this is a centripetal acceleration. It will be parallel to QA. It will be parallel to QA. So let's take here direction is parallel to QA, and what will be the sense? Sense will be towards the fixed point, towards A. Sense will be towards A. Okay, so now that we have defined this, let's see what other accelerations are left. So we have defined this, all three we have defined, we've calculated this, and now we are only left with this particular acceleration, that is tangential acceleration of q with respect to A. So at this particular point, we have reached the point QA in our acceleration diagram. So Q subscript A to the final point, that is Q1. So this is the vector in the acceleration diagram. And do we know how to find it? For this particular thing, for tangential acceleration, we will supposed to find the angular acceleration. So at this point we don't know about it. So let's see if we are able to guess what is its direction. So direction of this will be definitely perpendicular to AR, and we don't know the sense of at as of now, so we'll have to find it from the acceleration diagram. So at this point we have done all the calculations, required, and we can start actually drawing the acceleration diagram at this point. So we can see here that we'll have to actually start with this point. So O1 point we already have here, and you'll have to reach the point P1 by drawing a line parallel to OP for the length 88, and that's going to be towards O. So let's say here, so this is the line we need. Okay, so I'll have to take it over here. This is the direction in which we need our line, so we're just going to move this over to convenient point where you can easily draw that particular length. We have total length of 8, so 8 mm length. So this is where we'll take our starting point and draw 88 mm of length. So let's go ahead and take the starting point here, and we need to draw a length of 88. So 88. Fine. So all these fixed points will not be here, they will all be here at this point. And what we get here on the other end, okay, what we get here is the point small p, because okay, small p1. So this is the point we got. So you can see here that we have defined the length O1 P1. So O1 to P1 we have defined the length. Its length is 88 mm. It represents the acceleration of 87.8, which is rounded off to 88 meter per second square, and it's acting exactly parallel to OP and towards O. So this has been defined. Now we'll have to see if we are able to draw any other accelerations according to this. So next we can say from P1 we'll have to go to a temporary point QP by drawing a parallel line to AQ. So AQ is located over here, so we'll have to draw a parallel line to that. So let me take my protractor, keep it here, and I'll need a line parallel to this from P, but at this point I don't know the sense in which direction, upward or downward, it has to go. So I'm just going to draw a length for now, and on this we are going to get QP. On this somewhere we are going to get QP. So Q small p. Fine. So this is my point. Fine. So we don't yet know at what point it will going to be. We'll have to find the intersection of that with some other point to actually get it. So we are going to leave it at that for now, and then let's go for the next one. So we have the Coriolis component of acceleration. Its value is 33.8, which is rounded off to 34. It's got to be perpendicular to AR, and the sense is going to be towards the right. So let's go ahead and take perpendicular to AR. So I'll keep it parallel to AR for now. We also know its length. So what we can do is, instead of taking this particular acceleration first, we should draw this particular acceleration, and we know its direction is going to be this direction. So P1 is going to be located at this end. So P1 has to be located at this end, and the other end QP will be located at this end. Fine. So since we already have the point P1, we have to start drawing it in the backward direction over there. So we have placed it correctly. So now let's pick it and start over at this point. So from this we'll have to draw a length of 34. So let's go ahead and draw a length of 34. So 34 is coming up to here. So what we get here, okay, so since we are going backwards, we are going to get the temporary point QP. We're going to get temporary point QP here. So this is Q and this is P. Right, so we have already found this temporary point QP. So and what we can do with this line is we can actually take it over to here, Fine. So QP point we have found. QP point we have found. So QP point, okay, it's got to be coming back to P1. Let's come back to P1. I guess I made a mistake here. Mistake. The mistake is that this point here is not going to lead to P1. I guess it's going to lead to P1, but this point here is okay. So this is going to be Q1. So this has to be Q1. Or we could take it the parallel line in the backward direction, or is there something that I've done it wrong? I guess we got to take it in the reverse direction. So this is a bit confusing here. So Q1, the starting point. P1 is the starting point. No, that's the point Q1. Okay, so I think I made a mistake here. Because the starting point is Q, so we have to start at Q1 and we have to go to a temporary point which is P subscript Q, and then we have to start with P subscript Q and reach the final point, that is P1. So that's how it's going to be. So this point here, it's not going to be Q of P, it's going to be P of Q. So this is a point which we have defined, and from here, if we extend it somewhere here on this line, we are going to get Q1. Somewhere on that line we are going to get Q1. Okay, so but where exactly we don't even know yet, so we are going to keep it as it is for now. Next, let us see what other accelerations we found. So we have found the centripetal acceleration of Q with respect to A. So we have to start at A1, the point is defined, and we have to go to some point QA. We know the length and we know the direction and sense, so everything is known for this particular thing. So we have to go and do this. So it's got to be towards A. So it's got to be coming towards A, and it's got to be parallel to QA. So this is the direction we need. Let's go ahead and see that. So I'm going to keep it parallel here, and it's got to be coming towards this point. And what's the length? Length is 19.5. So just going to pick it at 19.5 mm. 19.5 mm. So 19.5 mm is going to be here. So okay, so between these 2 points, that's where I need to pick it. That point I need to bring it exactly here. Okay, and we got to go in the downward direction. So you can see here, this is the exact point, and that length you can see it is 19.5 mm. 19.5 mm. So when we come here, so from A1 we will be reaching a point QA. So I'll have to take this, and what the point that we got here is Q subscript A. So this is a temporary point, and from here I need to actually draw a perpendicular line to this, because then next acceleration is tangential acceleration. We know it's perpendicular to AR, so we'll have to take it that way. Okay, so I'll just take this and keep it in this direction, and have to take perpendicular in this direction. So this is the direction of the other acceleration. So now this line and this line, they need to both be extended till they meet at a common point. So the common point between them is Q1. Fine. So I'm just going to do a quick extension, and you can see they are both meeting at this particular point, and that point is Q1. That point is Q1. So what we got here is, okay, so these are all actual link lengths, so we're going to make it dark. This is the total acceleration over here, but what we have here are the temporary accelerations, and adding these will give us the total acceleration. So if you want total acceleration of Q with respect to the fixed point, or absolute acceleration of the point Q, and this is the line, the magnitude, the length of which gives us the magnitude. So now what we have to do is that since we got the point Q, we need to extend AQ to get the point R. We need to extend AQ to get the point R. So once again, we'll have to do a calculation which is similar to this little thing. So let me just write A1 to Q1. Fine. So AQ we already took, the length it is this. So acceleration A1 Q1 we need to take, and we need to find A1 R1 with the help of that. So A1 Q1, okay, A1 Q1, we got the length, we'll have to actually measure it. Okay, so let's go ahead and measure this. Okay, so from here I have to take this particular length. So what is the length A1 Q1? That's in the middle of 30 and 31. So 30.5 is what I'm going to take. So 30.5 mm is what I'm going to take, and this is the length which I'm supposed to find. So what I have to take is I have to multiply this with this and divide by this. Let's do that quickly. So 700 into 30.5 divided by 525. So let's do this in the calculator. Let's see what the length we get. So 700 multiplied with 30.5 divided by 525. That's giving us 40.7. So that's going to be the length. That's going to be the length to which we need to extend it. That's going to be the length to which we need to extend it. And what's that going to provide us? That's going to provide us the total acceleration. Total acceleration of the point R with respect to the fixed point. So total acceleration of the point R with respect to the fixed point, that is, let us say A. And in vectorially, how are we going to represent it? We are going to start at point A1. And we have to reach the final point R1. We are going to reach the final point R1. And this is the length. The length of this we just now calculated. Length of that is 40.7. 40.7 mm is the length. So we need to convert this back into the acceleration. Actual acceleration is going to be 40.7. Okay, 40.7. We'll have to actually draw it as 41, but we'll just take this value as 40.7 meters per second square. But here, since we have to round it off to the nearest value, because we at the most we can take 1 mm is the minimum measurement we can do. So 41 mm is what we're going to take it. So I'll have to start that. Again, I'll have to take this thing, I'll have to keep it parallel to this, and I need to extend my line up to 41. So 41 here. Fine. Fine. So 41. So that is going to provide us with the point R1. That is point R1. That's the point R1. And this length represents the total acceleration of point R with respect to the fixed point. Okay, so far so good. So we still have to find the acceleration of slider. And since we know that the slider is moving in horizontal direction, And with respect to the fixed points, so we'll have to just draw a horizontal line. So okay, let's say what is that acceleration? That is the acceleration of the slider. Yes, with respect to the fixed points, we can take any of the points of O, A, or G. So I'm going to write it like this, and vector notification is going to be from O1 to S1. We know the direction of this. Direction is going to be, horizontal. The direction has to be horizontal, so we are going to just draw this particular thing. We're just going to draw this particular thing. Okay, so it's going to go ahead and draw a horizontal line starting at point A1, starting at point O1 or A1 or any of the fixed points. Okay, so let's take our drop tool. We have to keep it horizontal, and we don't know the length of this, so we just want to draw a horizontal length for now. And somewhere on this line we're going to get S1. Somewhere on this line we're going to get S1. We don't yet know where exactly, but we know it will be somewhere on that line. So now we need to see if we are able to find some other accelerations, and we need to be able to draw them over this and get their intersection point with this line to finally have the total acceleration of the slider. So at this point, I guess we will be able to find the centripetal acceleration of of S with respect to R, so it will be starting from R1. Yes, so S with respect to R. So this is what we need to find. Vectorially we'll be representing it with the line R1 S1, and the formula for this will be velocity of SR, square of this, divided by the length SR. Velocity of SR, with respect to R. I guess we didn't find it, but we can just go ahead and measure it here. Velocity of S with respect to R is right there. Okay, let's go ahead and do the measurement. Velocity of S with respect to R, it's very near to 15. I could just keep it in between 15 and 14, so 14.5. 14.5 of length we have to take here. Okay, so velocity of S with respect to R, we're getting 14.5 in mm. So since we just need to convert it back, we have to divide it by 10, so we'll get 1.45 meters per second. So that is the velocity of S with respect to R. We have to take that here. How much did you get? That's 1.45. So 1.45 square of that divided by SR. Again, the length, we have to take the actual length, SR or RS, that is 300 mm. We have to take that length in meters, so 0.3 in meters. So doing this calculation will give us the acceleration, the centripetal acceleration. Let's go ahead and calculate it. 1.45 square of this divided by 0.3. So that's giving us 7 exactly, almost exactly 7. So 7 meters per second square is the acceleration. So now what's going to be the direction of this? Direction is going to be parallel to RS, and its sense is going to be towards some point. Okay, let's go ahead and see that. Since we already have the point R1, so it's going to be towards the point S, Okay, so we'll have to take a line parallel to that. So let's go ahead and take our tractor, and take it properly, take it correctly. So we need to keep it here parallel to this, and I need to take a line parallel to this, and we already got the point R1, so we got to go in this direction by length 7 meter per second square, so that's going to be 7 mm in this case. So it's going to be 7 mm in this case. So when we take that, we are going to reach a temporary point. And okay, so this is not the final point. This is going to give us a temporary point. That temporary point is S of R. Okay, the temporary point is going to be S of R. Okay, come on. Okay, I guess there's a problem over there. Let us save it, and we have to open it back. Fine. So we got this point. This point is S subscript R. So this is a temporary point that we got. Of course, this has got to be dotted line, and from here we need to draw perpendicular to this. I'm just going to take, okay, the protractor now, and we will need a line perpendicular at 90 degrees. So this is the line. So this line has to go and straight away intersect with this. Fine. So that will give us the final point S1. So this is a temporary point. And joining this to this will give us the total acceleration of R1 with respect to S1. So these are actual final accelerations. Measuring this length will finally provide us with the acceleration of our slider. Let's see what that length is. So we're getting 42 mm, exactly 42 mm. So okay, O1 S1 had told that it is going to be horizontal, and okay, so we're getting 42. So 42 mm is what we are getting here for this particular acceleration. Let's separate it, of course. And then when we need to convert it back, so we get 42 meters per second square. So that is our answer. That is the acceleration of our slider. Now there is one more thing that the question wants us to find. And that is the angular acceleration of link RS. Now we know the formula for the angular acceleration of RS. So actually the total acceleration is that the tangential acceleration of RS, we can find it by multiplying alpha with the length RS. So that is what we have to take. So tangential acceleration of R with respect to S. So what is the tangential acceleration of R with respect to S? So we have seen the centripetal component of S with respect to R, that is R1 to SR. So we have to take SR to S1. That is the length we have to take. So this SR to S1, this is the tangential component of R with respect to S. So we just need to measure it. Let's go ahead and measure it. So that's almost exactly 13 mm. So that's going to be 13 mm. So because 13 mm is going to be same in meters per second square. Okay, so is it same? Yes, of course it is same. So 13 meters per second square, that's the value of tangential component of R with respect to S. So that will be equal to alpha of R into S. Alpha of R is and into multiplied with RS. So the length RS is 300 mm. We have to take its value in meters. So that's the thing. So alpha of RS will be 13 divided by 0.3. So that gives us, okay, let's calculate this. 13 divided by 0.3, that's 43.33. So 43.33, and alpha is measured in radians per second square. So this is answer for our second bit. This is the answer for second bit. Let's maximize this. This is the answer to our first second bit, and this right here is the answer to our first bit. So I know the question was a very long one, and it took a lot of time for us to solve it. I don't know whether such kind of a problem will actually ever appear in the exams or not, but it's going to need a very long time for us to actually solve it, and you've seen it over here. So hopefully this kind of problem is not going to appear in the exams, because it's going to be taking a hell lot of time for us to solve it. But hopefully you have got a very good idea about how we'll be solving the acceleration diagram, acceleration problems using the acceleration diagram with this. So that's it for this particular video. We'll probably take up another video in our next session. Till then, see you. Goodbye.